This video is an introduction to the oceans. We know more about Mars and outer space than we do about some of the ocean regions because the oceans are covered in water. So there's a lot that we still have to learn about the oceans. Most of the ocean waters and the ocean floor in the world has not been explored. But we do know a lot. We know that oceans cover 71% of the Earth's surface, and they hold over 97% of the Earth's water. And there's really one world ocean, all connected. We divide them into five. The five oceans are the Atlantic, Pacific, Indian, Southern, and Arctic Oceans. But if ice, for example, melts in Greenland and goes off the Greenland ice sheet into the water, that ice will circulate around the global oceans to other parts of the world. So the five oceans are all connected. The Pacific Ocean is the largest, deepest, and warmest ocean. It's also the largest geographic feature on Earth. It covers 30% of the globe. If you look at the map on the screen, it shows you how wide the Pacific Ocean is, especially around the tropical areas. And that's one of the reasons it's the warmest, is because it's so big, especially in the tropics. And the tropics are the area that gets the most insolation from the sun, most energy from the sun. So that's a very warm ocean right around the tropics. The second largest ocean is the Atlantic, and it's about half the size of the Pacific, but much narrower. Take a look at the tropics in this picture. You'll see that actually Africa and South America are, relatively speaking, not that far from each other. The Atlantic is much narrower. It's also the saltiest ocean due to thermohaline currents, which come down from northern latitudes, bringing a lot of salt. The third largest ocean is the Indian Ocean. And if you look at the map, most of the Indian Ocean is actually located in the Southern Hemisphere. This is a little bit off from our usual perception because usually when we see the Indian Ocean, it's around India and South Asia. But that part is actually the minority. So the majority of the Indian Ocean is below the equator, and only a minority is above the equator around India. And it's eye-opening to think that over a third of the world's population lives in those countries around the rim of the Indian Ocean, which includes East Africa, Southeast Asia, Middle East, and Australia. That whole Indian Ocean rim is a very developing, very growing area of the world. The Arctic Ocean is the smallest, shallowest, and coldest ocean. It's up there around the North Pole. And 15% approximately is covered in sea ice. That ice doesn't show up on the map. And the reason it doesn't show up on the map is because there's no land up there in the Arctic. So the North Pole is not a piece of land that you can stand on. It's a piece of ice that you can stand on. But the ice is not actually on any ground. It's just floating. So when we look at a map like this, it's a little misleading in a way because it looks like a bunch of water we could kind of paddle through up on the very top of the world, but really it's frozen. And we say 15% is covered in ice, but that changes constantly. So in the summertime, the ice melts and the Arctic sea ice shrinks a lot. And then in the wintertime, it snows back in and then refreezes. And then the ice expands, and gets much, much bigger. So kind of like an accordion, it goes back and forth, these cycles from summer to winter of melting and refreezing up in the Arctic ice. How do we know there's nothing underneath the Arctic ice, that there's not any land down there? Now we have special imagery. We can see through the ice and see what's below. But even before that, people have driven icebreaker ships up through the ice and gone through the ice, and they can see there's nothing underneath it. You can still travel in the ship across the water as you go through that ice. There's no land below. Several years back, Vladimir Putin had Russia send a submarine under the Arctic ice and sent out a robot from the submarine with a Russian flag in its robot hand, and it planted it at the bottom of the ocean, a robot arm, and planted it at the bottom of the ocean directly under the North Pole. So Russia tried to claim the North Pole for Russia by planting a Russian flag. Now, of course, that's illegal. No one respects that international law, but that's what they did. The Southern Ocean, or the Antarctic Ocean, surrounds Antarctica. So this is the bottom of the world, and this is unusual because it's got a boundary that's a line of latitude, which is a circle, small circle. So the boundaries of the Southern Ocean is the circle of 60 degrees south. The study of the world's oceans is called oceanography, and it's a field that puts together many fields, biology, chemistry, physics, along with geography, hydrology, even politics. There's a lot of famous oceanographers. For example, Jacques Cousteau, the Frenchman on the left, who made films and showed life under sea to the world. And on the right is Deep Sea Dawn Wright, who is a professor and explorer of the oceans. And she recently went on a trip to the deepest place in the world, the Challenger Deep, in a submersible. And that's what you see in this picture. Her and the other guy went together down to the bottom of the deepest place in the world. The father of modern oceanography is actually from Virginia, Matthew Fontaine Maury. He wrote a book called The Physical Geography of the Sea. And that was a compilation of knowledge that he gained from looking at thousands of different ships' logs and charts. He was a Navy officer in the U.S. Navy. So he had access to all these documents from the ships. And by looking at them and analyzing them, he noticed many patterns about global winds and ocean currents and the ocean floor of the Atlantic. And he came up with a system of recording oceanographic data while on the sea for the ships could use much quicker. And that system became used around the world. And that led to ship routes becoming much safer and much faster. So Maury's ideas were adopted as the standard around the world. Here's a map from his book, The Physical Geography of the Sea. And you can see the ocean currents. They're running up the coast of Florida, the warm current, and it's running even up past Virginia, up at the top. The first comprehensive oceanography study was the British HMS Challenger Expedition. You can see the ship on the left, and it sailed from 1872 to 1876. The map on the bottom shows its route around the world. And on the way, it made hundreds of soundings. Soundings are measurements of the depth of the ocean by dropping a line with a weight on the end of it, like the ones you see on the right, all those weights hanging off of those lines. And you see how long the line is that you've extended down there, and you can see the depth from that. They also made over 100 dredgings. These are basically samples that you scrape off the ocean floor. So you have a container like the one in the middle on the right there, and kind of a little container at the end of the line that once you hit the bottom, you drag it across, and then it scoops up whatever's down there so you can sample what's down at the ocean bottom. So they made over 400 soundings and over 100 dredgings from all around the world. What the HMS Challenger Expedition was doing is called bathymetry. Bathymetry is a study of the ocean floor, its depth, and its topography. And a bathymetric map is a map that shows the ocean floor as if the water was removed. So if we had a giant vacuum and vacuumed out all the water from the ocean, and what's left we put on a map, we'd have a bathymetric map. Bathymetry advanced rapidly with the development of sonar during World War I. Sonar stands for sound navigation and ranging. It was used originally to try to spot German submarines under the ocean, U-boats. And the way sonar works is that we know what the speed of sound is. So we send sound waves to the ocean bottom. The wave bounces back. And from the time it takes for the waves to bounce back, we can calculate the depth. So by combining many of these sonar readings, many of these depth measurements from all over the world, now oceanographers began to discover chains of volcanoes and mountains and trenches and submarine plateaus all over the ocean floor, things they didn't know were there before. And this team, Marie Tharp and Bruce Hazen, took that bathymetric data coming in from sonar readings all over the world and put them together on maps like this one that you see in the background. That and the patterns on it, like the mid-ocean ridges and the submarine volcanic arcs, then helped lead to the theory of plate tectonics, because people realized that those features must be created by something, and they saw the patterns that these plates were creating those features. Today, they don't just compile individual sonar depth readings. They have multi-beam sonar, which sends many beams out across an area to map that wider area all at once, rather than just doing it point by point. Besides sonar, now today, satellites in space can see the sea by measuring the surface height of the ocean. They can measure the surface temperature from space. They can measure how much sea ice coverage there is, like on the picture on the right there, up in the Arctic. And they can even measure the depth of certain shallow oceans from space. So let's talk about the ocean's temperatures. You can think of the tropical oceans as the great heat storage units of the Earth's climate's heat. And why is that? Well, we know that the tropical oceans get the highest amount of insolation or energy from the sun. But in addition to that, they also have a very low albedo. They absorb 94% of the rays coming in, and only 6% are reflected back. So they're absorbing most of the sun's incoming insolation. But on top of that, the rays coming in from the sun on water, like the tropical oceans, they can pass through that water because the water is either transparent or translucent. So rays and energy from the sun can pass through and move further and further and further down and be distributed deep into the water, unlike land where it just hits the top. So knowing that, the fact that tropical oceans are these great heat storage units for the climate's heat, tropical oceans are projected to see the highest levels of sea level rise in the future from global warming because they store the most heat. And just to explain that, so it's not just the melting ice, that goes into the global oceans that causes sea level to rise. There's other reasons why sea levels rise. And one of them is that when water gets warmer, the individual molecules of water actually, besides moving around, called locomotion from place to place, they also do other types of motion too. They vibrate in place and they also rotate. They spin around and like this. So when water gets warmer, like in the tropics, then it starts to vibrate more and rotate more. And what that does is it puts pressure on its neighbors, and each molecule presses more and more, and the water expands or swells. So in other words, with the same amount of water, it takes up more space when it swells. And that happens when water gets warmer. So because tropical oceans are the warmest, they're going to swell more in the future and thus have the highest sea level rise. By contrast, the polar oceans, the Arctic and Southern oceans, are very cold. They're much colder. And there's three reasons for that. One is that we know they have a low sun angle. They get very low insolation from the sun. But besides that, they have the opposite of most oceans. They have a high albedo. Because the sun doesn't hit the water, it hits ice a lot of times. There's lots of sea ice floating on top of polar oceans. And that has a very high albedo, which reflects energy back off into the atmosphere. So that energy doesn't warm the oceans. They stay even colder. And then third, you have icebergs breaking off from polar ice sheets, which float on the ocean like giant ice cubes in a martini, and that chills the ocean. So because of the lower insulation, the high albedo of sea ice, and the icebergs breaking off from polar ice sheets and chilling the ocean, you get very, very cold oceans in the polar oceans. There's a very important concept related to global warming and the polar areas called ice-albedo feedback. And ice-albedo feedback is an example of something called a positive feedback loop, which is found in science. There's positive feedback loops and there's negative feedback loops. So just to be clear, when we say a positive or negative feedback loop, it has nothing to do with whether the result is positive. Like if it's great, it has nothing to do with that, or negative. It has to do with what one change causes in another change. So a positive feedback loop occurs when you have one change A, that causes a second change B, and then change B creates more of change A. So each change causes the other, and they both go up. A negative feedback loop would be if you have change A, it causes change B, but change B actually causes not more of A, but less of A. It negates it, and therefore would be a negative feedback loop. It kind of stamps it out. Okay, so this is a positive feedback loop, the ice-albedo feedback loop, where one change creates another, which creates more of the original. Let's see how it works. So if you look at the picture, what you see is a sequence across from left to right of the process of ice melting on the ocean in the polar areas, losing sea ice as, let's say, global warming takes place. And if there's more warming, then the ice melts more, right? So you're losing ice on the ocean surface. And by the end of the last picture, there's no ice left at all. Okay, so you went from a lot of ice on the left to a little bit of ice to no ice on the right. And you can also see that the ocean's albedo has changed during that process. So albedo is represented by the character alpha. See up in the corner. So it's on a scale from 0 to 1. So 0 is total absorption of all the sun's rays, and 1 is total reflectivity. It's the highest albedo. So the original albedo, when you have lots of snow and ice there, on the sea, you can see the albedo, the alpha is 0.9. That means that 90% of sun's rays are just bouncing off, going back out of the atmosphere. And you can see at the bottom, only 0.1 is getting through to the water. And then the second picture, you can see half the rays now are bouncing off because you lost a lot of the snow and ice at the top. So the albedo is lower and half is getting through. And the final picture, you can see that all the ice has now melted. And so now it's 94% of the energy getting into the ocean and only 6% is bouncing off. So you have a total reversal of albedo from a high albedo to a very low albedo because of the loss of sea ice. So what's the ice albedo effect? What's the ice albedo feedback loop? Well, it's basically a feedback loop, a positive feedback loop of that process. In other words, change A is the melting of sea ice, which is happening across this sequence. Change B is the change caused by change A. Change B is the loss of albedo, the lowering of the albedo of the oceans. So loss of sea ice causes lower albedo. And then that change B, a lower albedo, means more energy is coming into the oceans, which means they're warmer. But warmer oceans are going to melt the ice even more. So you're going to have even more of change A, more melting ice. Okay, so melting ice creates lower albedo. Lower albedo creates even more melting ice. So that's a positive feedback loop. Each change causes more of the other, and they both increase together. So that positive feedback loop, that ice albedo feedback, the importance of that is that that's the reason why the polar regions are warming at twice the speed of other places in the world. Polar regions are warming at twice the rate of other parts of the world. And it's because they're the ones covered in sea ice normally. And then if they lose that sea ice, then all of a sudden the warming really speeds up. And that's what's happening. Let's shift gears and talk about politics. Who rules the oceans? It's a good question. And it's hard to answer. It depends where you go. And sometimes it's hard to say. But in general, there's a UN agreement called the United Nations Convention on the Law of the Sea, UNCLOS. And under that agreement, there are certain accepted boundaries of international waters. First is territorial waters. These are the waters that are typically 12 nautical miles off a country's coast. And you have exclusive economic zones, EEZs, which are 200 nautical miles off the coast, that whole zone. And then the high seas is everything beyond the 200 nautical miles out in the open ocean. And that's owned by nobody. It's no country, and it's very difficult to regulate. So the territorial waters up to 12 nautical miles off the coast are not just controlled by a country, not just the rights of the country, but they are the country. That is the country. It's part of the country itself. In other words, it's called territorial waters because it's actually part of that country's territory. So, for example, if another country sends a ship, if there's a foreign ship that sails into your territorial waters unannounced, you can shoot that ship because it's technically just invading your country illegally. Then the exclusive economic zones, those are areas where a country has the rights to resources in that zone. So up to 200 nautical miles off the coast, the country has the rights to the resources like the fish or the oil and gas or minerals at the bottom of the ocean, things like that. Those things belong to the country, but it's not technically your territory. It's not part of your country. So if you look at this map on the screen, you can see all these buffer zones that are drawn around all these countries and islands and everything. Those are all the exclusive economic zones, 200 miles, 200 nautical miles off each coast. And one important thing about that is that you can see it really pays to have islands. So countries that have a lot of little islands like Britain and US and France, et cetera, they have little island territories around the world like American Samoa and Saipan and all these things. These are very valuable because they give the country all the waters 200 nautical miles around that little island. So even a little blip of an island, if it's recognized internationally as an island, as a real part of your country, then you get all those waters around it as your the rights to all the stuff in there. A good place to look at EEZs today is the South China Sea. It's a real hotspot for conflict and disputes about exclusive economic zones. And specifically, if you look at this picture, you can see the blue dashed lines indicate the exclusive economic zones, the EEZs, for all the different countries around the South China Sea. And there's a lot of them. There's Malaysia, Indonesia, Brunei, the Philippines, China, Taiwan, Vietnam, etc. All those blue lines are their EEZs, 200 nautical miles off their coast. Now, if you go 200 miles off of two different countries, often they bump into each other only 100-something miles in or 50 miles in because they're really close. In that case, what they do is they just find the midpoint usually and split the difference. But in the South China Sea, China today does not accept these exclusive economic zones. It says that based on old Chinese maps from hundreds of years ago, it has the rights to all of the South China Sea, which is all of the areas in the red dashed line on the map. That line is often called the 9-dashed line because on older maps from China, it's portrayed with 9 dashes. So basically, China just does not respect other countries' EEZs in the South China Sea and doesn't believe that they're valid. This was tested in the United Nations in 2015. The Philippines took China to arbitration in the United Nations and charged China with fishing in its waters. They had all these Chinese fishing ships in Philippine waters and many other countries' waters too. But this was about the Philippines. And China lost. It was obvious that they were fishing in the Philippines waters. But China said they don't accept the ruling, meaning they don't accept that they don't have a right to do that. So China's playing by a different set of rules in the South China Sea. And this whole area, all the EEZ disputes there, is a big issue to keep your eye on in the future. China's also building artificial islands. They're taking sand from the bottom of the ocean and dredging it up and then hosing it onto existing coral reefs, little blips in the middle of the ocean. Like you see, it says the Spratlys and the Paracels. All these teeny little islands, they're building them up, and then they're putting military bases on top with helicopters and soldiers and bases and stuff. So that's totally illegal in international law. You can't make land like that in the middle of the ocean and then claim it, but that's what they're doing. And in general, this sea, the South China Sea, which is part of the world oceans, is very pivotal because 1/3 of the ocean traffic in the world with cargo in it travels through the South China Sea. It's the bridge between the Indian Ocean and the Pacific. So it's very important for the future. Now let's turn to the structure and regions of the ocean and the ocean floor. We can start with the continental shelf. The continental shelf is basically the end of the continent, okay, the end of the long continent. And then its last little bit there, the edge of it, is underwater. This is the underwater edge of a continent. And it sits like a shelf over the rest of the ocean below. Continental shelves can be wide or it can be narrow. Generally, the wider they are, the longer a trip a wave has to travel to get up it, to get onto the shore. And so the waves are smaller where there's a longer continental shelf. So, for example, the east coast of the United States has lower waves because it's a much longer continental shelf. The west coast, like California, has bigger waves because its continental shelf is much narrower. Now, I want to point out that there's two terms that sound a lot alike here. I want to distinguish them. There's a continental shelf, but then there's a continental slope. They sound very similar. Okay, so continental shelf, you can see up towards the top, but then at the end of the continental shelf, it slopes down sharply, kind of like taking a slide down to the open ocean floor, and that is called the continental slope. Okay, so the shelf is up here, then it slopes down. That's the continental slope. So if we slide down the slope, then we reach the open ocean floor, and that's called the abyssal plain, deep ocean floor. So shelf, slope, abyssal plain. The abyssal plain is dark, and it covers 70% of the ocean floor. It's the largest habitat by area on Earth for species. Now that we looked at the ocean floor, let's look at the actual waters of the ocean itself. So we can start up at the top with the coastal waters. Those are the waters that lie right on top of that continental shelf, that more shallow area there. And the coastal waters are home to 98% of the life in the ocean. That's largely because they're so shallow that there's lots of sunlight and oxygen available from above. So you can have a lot of plants growing there, including under the ocean, on the ocean floor, and you can have other things feeding on those plants. Also, coral reefs live there because coral needs sunlight, and coral actually grows upwards towards the sun. So it tends to live on the shoreline and tends to grow up, up, up. Inside the coastal waters, beyond that, towards the inland areas, is the intertidal zone. Intertidal zone is just like it sounds. It's the zone between tides, between the low tide mark and the high tide mark. So when the tide is out and it's low tide, then all the sand is exposed, along the beach there. And then the tide comes in and covers it all up in water. And so that area in between that's sometimes underwater and sometimes exposed is the intertidal zone. It's a place where crabs and starfish hang out and mollusks and things like that. And all those species are adapted to live in water and also to live in the land. And if we go out beyond the coastal waters to the open ocean, that's called the pelagic zone. The pelagic zone is far from the shore and it's far from the bottom. It's out there on the open ocean. And the pelagic zone is where we're going to find the biggest fish, the biggest schools of fish, whales, squid, and you'll even find pelagic birds, which are birds that fly out far over the ocean. And if you look at the diagram, one thing to notice is that there's a layer on top of the ocean which is receiving sunlight, and that's called the photic zone. The photic zone is receiving sunlight, so that's where your plankton are going to grow because they need sunlight. You go beyond the photic zone, it becomes dark. So now if we were to dive down vertically into the ocean, we would start to see the energy fade out, right? As the light fades out, the energy fades out the deeper we go. And about 200 meters down or so, we start to see all the sunlight disappear, depending on where you go. And pretty soon we'd reach a layer called the thermocline, where the temperature is going to drop steeply. And you can see that in a diagram. Red is the temperature. So you see the temperature is warm, 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 warm. It gets to the thermocline and then cold, 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 cold after that. It's called the thermocline. Thermo as in heat, and cline is a root word that means like a slope. In this case, it's a decline, a downward slope. So it's a decline in temperature, a thermocline. So the thermocline layer is the layer of the ocean where the temperature starts to drop steeply. Fish can't live below the thermocline because it's too cold, and also because it's so deep that there's not enough oxygen down there. And fishermen often like to know where the thermocline is because they don't want to try to catch fish below it. They're not going to find anything. So let's look at the ocean food chain. The food chain in the ocean literally starts at the top, and it starts with plankton. Plankton is a general term for ocean organisms that cannot swim against the currents. They are carried by the ocean currents. And they mostly just hover across the surface. They can move a little bit, but they hover and they float, and they're located in the top 2% of the ocean waters, up in that photic zone where the sunlight is. And you can see on the diagram there's two types of plankton. There's phytoplankton and there's zooplankton. The phytoplankton is plant plankton, for example, algae or microscopic diatoms. And zooplankton is animal plankton, like krill or a jellyfish. These can be all different sizes and shapes, from microscopic to something that's, a foot wide or even bigger than that. But of those two, phytoplankton and zooplankton, the phytoplankton, the plant plankton, are the critical foundation of the food chain, just like plants on land. If you get more phytoplankton, you feed the food chain and you get more ocean life in general. They are primary producers. Phytoplankton make their own food, just like grass or trees. And they use photosynthesis to make their own food, but that requires nutrients. So where do the nutrients come from? To understand that, we have to understand two concepts: marine snow and upwellings. Marine snow is not actual snow, but it's like snow, the shower of nutrients and debris that falls from the upper layers of the ocean to the bottom. So dead animals and plants, or waste or dust, all the stuff that falls down. Think of all the animals living in the ocean, all the species in the ocean. And when they die, where do they go? Does a truck come by and pick them up? No, they just fall to the bottom, right? And so you've got this massive repository of nutrients on the bottom of the ocean down there from all this dead stuff. And that includes carbon, nitrogen, phosphorus, all these big elements that are necessary for life. So the question is, if the plankton are the foundation of the whole food chain in the ocean, and they live at the top, but the nutrients are what you need to grow and they're at the bottom, how can we get the nutrients at the bottom up to the top? Because if you could do that, then you could really feed those plankton and the whole food chain would go nuts. You'd have lots of life in the ocean. Luckily, nature has a way to do that. It's called an upwelling. So upwellings are periodic movements of colder, denser water from the ocean bottom up to the surface, just like it sounds. It's upwelling, like this. And what allows that to happen? Well, basically, there's different ways of creating an upwelling. But in nature, a lot of times an upwelling happens because of wind along a coastline. So if you look at the red arrow in the picture, that's wind moving along a coastline. And it's basically sort of pushing or wiping away the upper layer of the ocean there. The top layer of the ocean is being wiped or pushed away by the wind. That removes it and opens up a space that the cold, dense water at the bottom can then fill, can come up and fill that space. But remember, that cold, dense water at the bottom, that contains all those nutrients that we just talked about, the nitrogen, the phosphorus, the carbon. So basically, you're bringing food to the top. And you might also ask, why does it rise? Well, remember, we said back in the weather section that things that are cold under higher pressure. And so things that are under higher pressure want to release into lower pressure. And that's what happens. You have this cold water that's under pressure. Now there's a space above it. It wants to release up there. So it wants to expand upwards, bring those nutrients with it. And when that happens, when the upwellings bring nutrients to the top, then you get these big phytoplankton blooms. The phytoplankton really expand and reproduce. And that allows fish to come in and basically feed on all that plankton. And you have a feeding frenzy. Basically, the zooplankton and some small fish eat the phytoplankton. And then bigger fish eat the zooplankton and the small fish. And the food chain goes on from there. These phytoplankton blooms can be so big that you can see them from space. This is a space image from Washington State, the coast of Washington State on the west coast in the Pacific Ocean. You can see all the phytoplankton covering that coastal region. When the fish that eat phytoplankton hear that there's a lot of nutrients coming to the top and upwelling, they get the message and they show up in droves. The sardines, the anchovies, they have a feeding frenzy, like in this picture. Half of the fish that we catch worldwide are caught in upwelling zones. So, for example, Peru on the right is a gigantic fishing industry. And the next time you see a can of anchovies, take a look and it's likely to say product of Peru, because Peru is one of the biggest anchovy producers in the world because it has so many upwellings there in that red buffer zone on its coast. There's also a downside to phytoplankton blooms. If you have too many nutrients, for example, if you have lots of farm agricultural runoff that crosses over the land and washes out to the ocean, all those chemical fertilizers are feeding the phytoplankton. The phytoplankton can go nuts, and you have what you call a phytoplankton explosion, meaning way too many phytoplankton. And phytoplankton explosions can be dangerous for ecosystems because they basically clog up the photic zone at the top of the ocean, that sunlit zone, so the sun can't pass through. And so when the sun can't get into the ocean, then all the plants that are supposed to be living on the bottom of the lake or the ocean, or whatever it is called subaquatic vegetation. It lives in the bottom of the ocean there on the coastal waters. It can't grow because there's no sunlight for photosynthesis. So you lose that, and it's a foundational part of the ecosystem on the coastal waters. And then lots of the food chain then disappears. So these phytoplankton explosions are a big deal. If you Google them, you'll see lots of examples around the world of communities from China to Africa to the Great Lakes in this picture, Lake Erie, that are battling against phytoplankton explosions. So in the big picture, We've come a long way in exploring the oceans in the last 150 years, and future ocean exploration can help do a lot of things. It can help reveal new foods and medicines that can help people. It can predict natural disasters better, like earthquakes and tsunamis. It can reduce pollution and environmental damage, for example, from overfishing. So, from animals and plants to the environment and people and cultures, our future is connected to the oceans.